Okay, I think I can start. So I'd like to go through what kind of universe do you want? And so this was kind of a basis of something I generated for a continuing education course. And in that course, there was kind of a mix of students. Some of them had PhDs in various technical areas. Some of them were in their kind of like 80s and just wanted to know, very curious about things. And so it was kind of a mix. And so I kind of went through kind of the Big Bang kind of sequence and development of stars and galaxies and planets, but I wanted to come up with something a little bit different. Because I think a lot of people have been familiar with that, wanted to see something. And so I came up with this, and before I go on, I just want to say, what would you answer to a question like this? So one of the answers I got in this course is they would like to have a chocolate universe. So yeah, and so this is more of what kind of things do we need in the universe to kind of have the universe that we have in terms of the complexity type of things. So I know, Todd, you're kind of working in this area. There are a lot of other people that are generating deep philosophical things on quantum mechanics. That's not what this is. There's some ties to anthropic principle, pretty much on the parameters we'll get to later, but that's not the majority of what I have here. So wanted to just kind of go through this with no equations, just kind of have a discussion with this group, kind of to see, what's out there and, how is it kind of the forces that are out there, what are they actually needed for when we, talk about the universe in general and how we came to be. And so large questions to ponder, why is there universe? Why is there only matter? How unique is the earth? How did life begin? And so on. So a lot of these are there, but one at the bottom, one from a quote from Carl Sagan, we are a way for the universe to know itself, right? I mean, the whole history of the universe is kind of in the human mind and being shared, and we can only kind of reconstruct things based on kind of the information that we have. And I always find it just astounding that we people can make these measurements and come up with these kind of conclusions, as Todd just showed, in terms of the dark matter problem. A lot of measurements being made in trying to come up with things and trying to connect on how they all kind of fit together to solve that particular issue or question. And so instead of starting from the Big Bang and going around to us, kind of a more approach is to reverse engineer that, right? So reverse it and then kind of ask what kind of forces, particles, parameters, rules, and what kind of life is kind of expected, and how does it relate to those properties of the universe. And so what would you think would be a physicist's first guess at universe's behavior, right? If you took a course in physics and you came up with the second law, thermodynamics, energy conservation, maybe even a little bit further in terms of matter and antimatter being generated. So this would be probably my first, answer to that. Pretty much nothing, right? It would either disperse out and, just like a gas, or, we wouldn't have any matter at all. It'd just be kind of this radiation. And we still don't know the answer why there is a matter, or maybe things just clump together very quickly into black holes. So it's kind of a fine balance in there. And so first answers to this question is probably want a universe not like the typical physicist would design or think about. Right. And so we want to look at some reverse engineering, some basic requirements. So we want some energy involved in there, right? We don't want it to be, Big Bang and just thermodynamically there. We want it to store some energy, right? So that it can be used for later. So we want to eventually to go out of thermodynamic equilibrium. We want planets with water. So we want variety. We want different elements in there and different molecules. We want to live enough, stars to live enough for life to evolve, right? And so some of the early stars, that was not true, right? Big stars, you know, don't can evolve very quickly, generate some of those elements, some of that variety, but they don't live long enough for life, at least how long it took for life on Earth to evolve. And we don't want it to be too dangerous, right? Things out there are quite dangerous, right? Things are colliding and exploding out there and wiping out atmospheres and planets. And so we don't want that to be too dangerous. So what we need are the right forces, particles, properties, and rules kind of to at least get some of these requirements satisfied. So what about the forces? There's four major basic forces, but let's think about, what we want and how they are generated. So we want matter to clump together, which is not our typical way of seeing things, right? Usually when we release something, it disperses out into the space that's there. And so we want things to clump together. And so that is gravity, right? It's long range, right? Works at long distances. We just saw this analysis of galaxy rotation and ways the galaxies collide and the effect of gravity on that. We want some stored energy to create temperature differences. So that's usually the strong nuclear interaction, right? In the Big Bang, it was first 3 minutes that helium was kind of created along with some lithium and deuterium. And it was pretty much determined by the half-life of the neutron uh, in there. And so if that went longer, you might imagine that everything might either be clumped together into these elements and you might have no hydrogen left, or maybe it didn't last long enough, and you would have hydrogen, which would probably be okay for later development. So we want these stars, eventually that generates that are clumping together. We eventually want them to be rather long-lived, right? And in the first estimate, the first stars, that was not true, right? And so you can imagine, the first 3 minutes, there was a lot of nuclear interaction, right? And so a lot of helium was generated. So nuclear forces can really react rapidly. And so why don't stars just kind of generate these nuclear reactions for 3 minutes and then kind of explode, right? Well, they don't generate neutrons for one, but also there is a weak force in there which needs some change in the charge to actually generate something like a neutron. And it takes a little while for that to occur. And so the weak nuclear force is kind of tied to this long-lived stars. And then we want different Legos, kind of like to stick together and do interesting things with long-range forces. That would be electromagnetism, which is kind of a very subtle type of force. And we'll kind of take a look at that here. So we have the clumping together, right? We've kind of seen that. Gravity is the one that the force we're most definitely involved with and know a lot about. But obviously physicists really, haven't really cracked the code yet. A lot of progress has been made on that. We want to have the different particles. So we want something heavy to give a mass, but something light, but of opposite charge to take the volume. And so, if you look at the standard model of physics, you don't see that, right? The there's some heavy particles, but they're not the ones that are typically around. They'll decay. And so you look at the stable particles in there, and you won't see ones that are necessarily too heavy. And so what is that? Well, it's, the quarks are basic fundamental particles in there, but they can't really stand by themselves, right? It was a very fundamental question very early on. And so they'll have to combine. And so you combine three small masses and you end up with something very heavy, comparatively very heavy, the proton. And it's not due to their individual masses, it's just due to the well and kind of the speed at which the quarks travel inside the proton that give that mass. And so even the proton mass is kind of a secondary thing and very interesting. Then you have the electron, which balances that charge balances exactly, but there's some separation, right? Just a little bit of separation. It doesn't all combine down together as once at first thought. And then you have something that the particles can exchange, and that's light. And we know that that's a long-range force because we can see very deep into the universe. And so I had a diagram there of the atom. And then we want this almost balanced forces, right? If they collapse all the way down, it'd be completely balanced. But it's these subtle effects of electromagnetism that really generates just a lot of the different properties out there. So subtle effects of the polarization, sharing of the electrons that generates, chemistry and molecules, various types of materials, and so on. So then we also want a loss of equilibrium early to store the energy for later. So this is kind of the temperature in the universe versus time. It comes down, this time is all relative here. This first 3 minutes kind of here. This is 100 million years or so to the first star formation. Peaks a little bit later, I believe 2 to 3 billion years after the Big Bang. And so it comes down rapidly. Things have to cool off enough, right, to actually have star formation kind of start up, right? It has to cool enough. And so that's where some of the molecular things get together. Some hydrogen molecules can form. Now they can spin, and now they can cool a little bit faster, kind of causing star formation. And later, as the heavy stars kind of form and explode, they generate metals, or meaning other elements that can later go into planet formations. And so it's the two energy potentials that are out there, right? Gravity, because things are spread somewhat evenly, a little bit of ripples out there, and also all that nuclear potential, because hydrogen is out there, and when you combine the two hydrogens, you get energy out of it. So this is kind of the relaxation of those two energies, extracting that energy left over from the Big Bang. Then we also want to have the ability to measure. That just means that we want, the light to be massless, so it can see a long ways and not being obscured by anything, so we can make measurements on it. And then in the solar processes, which really require a lot of the combination of various forces, obviously the strong force is where the energy comes from. Electromagnetic is kind of how the energy goes out from the star. Gravity is kind of what initiates the whole heating process as the cloud collapses. And remember, the weak force kind of is important in that nuclear process, kind of to slow things down a little bit. I remember that's tied to the neutron lifetime that was involved in the nucleosynthesis during the Big Bang. And so then we get this variety of elements, of Legos out there from this. And what that gives us with just considering these forces is an array of sizes out there. And so this goes from the universe kind of through various astronomical stages, to human scale, to life scale. And this was written in Journal Big History a little while ago. And it's somewhat of a constant ratio. It's pretty much a ratio 140,000. I like to think of it, you hold your fist and you have someone in a plane at cruising altitude. The ratio of 140,000 would be the length of your fist compared to the altitude of that plane. So this is just a few steps in there, pretty much like 7 different steps from the universe kind of to the nucleus. So there's various things with the cooling aspects. It's typically around a factor of 1,000 in energy as things cool down. And so these processes are well kind of separated, right? When we have a chemical reaction, we don't necessarily want to have a nuclear reaction going on at the same energy, right? That would be kind of messy. And so, we want to have these energy scales well separated. And then the rules kind of know that physics is not really intuitive. So showed Aristotle and Galileo kind of, saying what keeps things moving, right? If you look at things moving, you push something, it eventually stops kind of right away, except in space or on ice. And those were the two that kind of led to some interesting discoveries. And so you don't want things to be deterministic the way people thought after Newton, people thought things were very deterministic. You want a little bit variation in there. And so you want to have things acting more like waves with quantum mechanics in there to generate a little bit of uncertainty. And this comes to eventually this laziness and anarchy that I'll come back to in a couple slides here. Next slide. And so we want the quantum area to help. We want waves, so we have an uncertainty. We want spin, which gives us a lot of good chemistry. We have tunneling, which allows reactions to happen where they would not usually occur, for example, in the stars. And we want some symmetries that are tied to conservation. And so a lot of this information at this point comes from, I think, this very nice book by Peter Atkins, Conjuring the Universe. It's actually a chemist, a quantum chemist, and he looks at these various things. He pretty much says, anything goes. And so nature is very lazy, and pretty much anarchy rules. For example, the case, kind of the physics went from A to B at a certain time. You might think, well, how does a particle go from A to B, right? Well, okay, you could throw a ball, sometimes you have to get arc or whatever, but it says, in the quantum world, it's every single path, right? Every single path it goes, but it's a wave. Because it's a wave, it'll interfere at getting this particular location. And it's that interference that causes the most likely path. And so it's a fundamental principle of the physics. So it's like, which way does the particle go? Every way, right? And then it's a wave, and you can figure it out. And then how do you get the forces, right, from this wave type of principle, right? And so this goes a little bit further, is that it's a symmetry. And so instead of changing the phase of the wave at each point, right, you move the trough to the peak and so on. Well, if you make that arbitrary at each one of the locations, and you require the symmetries to be maintained, you come up with, in this case, electromagnetism. And so, it's a very simple, kind of not straightforward, I guess, but simple way of kind of the way that the rules and the laws and the forces kind of just come out of this process of somewhat of anarchy. And then the anthropic principle kind of ties to this parameters as to how strong things are, what are the masses, And so there's been various kind of discussions on this. So how many dimensions? Are there multiverses? But a lot of number of leading physicists have thought about the self-aware universe, including John Wheeler, Paul Davies, and so on. And there's a good discussion of anthropic principle in Clement Vidal's book, The Beginning and the End, which you can find free on the Physics Archive. And so the idea there is that there might be some type of connection from some consciousness looking back at the origin. So here you see Big Bang kind of on the right-hand side, evolving to an eye that then looks back at the Big Bang. Obviously, this is very speculative, and a lot of people have been thinking about it and continue to think about it, but still, out there. And so also quantum mechanics affects life. And this is where it becomes very difficult. You can have, for example, anytime you have a heat gradient, you can have some automatic system formation. For example, boiling a pot of oil, right? You can generate a lot of different structures in there. And some people have said that is kind of similar to what happened perhaps on Earth. And this is what I give them for beginning to consider the log scales in evolution. So what is your life on a log scale? So remember, when I teach this, a lot of them are older age, and so they know. And so if you're born, you kind of figure out, okay, that's 0.75, 9 months that you took to develop to that far, right? So the age is at, you're born at age 0, but then you take 3 times kind of the previous one, and you see kind of steps in age 1.5 when you walk and talk, 6 where you start to be social in school, 19 where you're kind of an adult, and then 60 where you're at least thinking of retirement, if not already there. And so this is just a logarithmic scale of kind of the periods of life. And then I kind of extended that a little bit further because one of the main questions is, well, how does the lifespan of a human compare to that of the universe? So you might say, well, where does that come from? If the rate of acceleration is geometric, so it's quickening by a certain factor, you want to know that ratio. And so I started, we could get the ratio of the universe, we can kind of estimate that simply, and then we want to compare it to human lifetime. So there's a lot of assumptions in here that had to go through those different stages in life, allometric scaling from bacteria, then what is the constraint on the bacterial growing type of period. And you can see that it gets quite complicated. And if I take the log, we get 18.5 in terms of the log of that number there, the number of steps. And so that is quite interesting. So it's pretty much twice the number of order of magnitude, 15 billion years to 100 years for a human life. So this was just another way of taking a look at this with a different perspective. Sometimes I just wish the answer would have been chocolate, just to make it easy and be much more fun. But we got through what are the needs for the forces, the particles, and the rules. How, a lot of these rules just come up laziness and anarchy out there. They're not, there's a lot of math that goes with it. But it's kind of the fundamental thing of, these considerations. And evolution taking advantages of amazing variety and combining things at different levels for the different sizes. And then, the speculation, is this, coincidence in some way? And so, obviously Wheeler and Paul Davies have speculated on that and continue, and that's still an open question to be worked on. All right, thank you very much.
Okay, thank you so much, Dave. I guess maybe if I could ask Dave and Ken and Todd, let's pull up chairs so that you're sort of available. We'll open the floor to anyone who has a question. And again, anyone on the internet, if you can unmute yourself, just go ahead and ask your question. We will be able to hear you here. If you have a question, it would be probably the best if you'd be willing to come up here and speak into that microphone so that people on the internet could hear you. So please come on up if you're willing, and I'll just stop and let the conversation develop.
Well, both the last two reminded me of something that may even be relevant. In graduate school many years ago, my field is religion. We had a program called Methods of Studying Religion. And we had 6 or 8 methods. We'd study it historically, and there's one picture of religion. Then philosophically, that's a different picture. Now you can include Buddhism, Stoicism, so on. And then theologically and sociologically, and on and on and on. We had about 7 methods of religion, and the conclusion of all this was that religion seems to be the composite results of many methods, only 7 of which we can now identify. That felt right, and that feels like it's the same sort of thing here with the universe. Is that?
Well, yeah, thanks.
Yes.
Sorry, go ahead.
Could I make a comment?
Yeah, go ahead, Andre.
Yes. No, actually, I wanted to make a comment with respect to Ken Solis' presentation. No, actually, I think Martin van Dijn is here. He could also make this comment. But actually, I would like to bring attention to recent research by Martin van Dijn, which showed that criticism of free energy rate density as a measure of complexity could be even more serious than what was spelled by Ken Solis. No, Ken Solis spoke about kidneys having the same energy rate density as brain. No, Martin van Dijn showed that actually kidney have 3 times higher free energy rate density. So if you follow Chason, we should say that kidney is 3 times more complex than brain. No, so it shows clearly that really we can free energy rate density is extremely imperfect measure of complexity. So brains of mice are not have the same free energy rate density as human brain. It have significantly higher energy rate density than human brain. And no, he showed also that Roman Empire at the very beginning had higher free energy rate density than when it was the most complex. No, so I think no, Ken Solis was generally correct, but he's perhaps underestimate how much correct he is. So Martin van Dijn shows that free energy rate density have even much more serious problems with as a measure of complexity. No, so I think we can more or less forget about Chason's era in big history research and perhaps move to some new era. Thank you for attention. I think Martin van Dijn, who is here, can say if I was correct or not.
Yeah, I will show some examples in my own presentation in a few hours. So maybe I'll come back to your points, Andre.
Yes, so it's a sort of advertisement for Martin van Dijn's presentation. So I think I would also, I think everybody who would come to Martin van Dijn's presentation will appreciate the new interesting data which he presents.
Yeah, one of the overriding things about use of energy for complexity is the task at hand. So another example where, I have to say that Cosmic Evolution, I think it's a fantastic book. It's just on critiquing the energy rate density arguments. So one example too is he states that while flying, Derek Chaplin does, that flying occurs in a three-dimensional space rather than walking in a two-dimensional. So therefore flying has to be more complex because it has to deal with a 3D complex environment. However, there's just simply the work of flying you got to consider. So similar with a kidney, a task is going to use more energy than a brain. It's the tasks at hand. The kidney is a very complex organ and how it filters your blood. For those who don't know, I'm a physician. But anyway, you got to look at the task at hand. Sometimes the task at hand simply requires more energy than mass. You know, end of story. It's like swinging an axe versus hand sewing. Now, the hand motions of, you know, doing the sewing or writing a novel, very complex. But the task at hand doesn't require much. You have to move a 1 kilogram axe back and forth. So anyway, yeah, thank you, Andre. So you're bringing stuff, and I'm sure Martin will as well. It's the task at hand, many times it overrides the energy needed to sustain and do the processes of a complex system.
Yeah, I think there's been a lot, Martin and others have done a lot of work on the energy rate density, free energy rate density. But, based on Ken's talk, it was more of the energy flow through the system. And I think that's much more important than the density. In fact, I think even though energy is easy to measure, the density is a thing that's very difficult to measure. For example, Martin will speak with the Roman Empire, as we talked about earlier. The question is, well, what is the mass of the Roman Empire? Right? Is it just the mass of the people in there, or the mass of all the buildings in there, all the roads, whatever? And so I think it has to do more with the operating system. What is the energy flow through the whole system? And so, yes, energy density does have, a part to it, because as we, use more and more interesting energy sources, they tend to, we tend to be more efficient and use some things. But it also means collaboration, right? Not just of the humans, but the humans in the society and how they're organized. So I think, that's one thing that I'm kind of taking a look at. The problem there, of course, is, well, how do you define a system, a collaborative system, right? And so you trade one problem for another, but I think it's kind of more to how they can coordinate the whole energy flow. And so I'd like to get back to Davidson's question and point in there. I think that is very true. And so, when looking at evolution and, of a person, right, there was a good kind of set of articles, Borgie Exted, who we have, wrote a paper on complexity for the journal. But he had looked at, the development time and the evolution time, and three kind of phases in there, kind of reproducing the biological aspects when the heart forms and lungs form, evolutionary wise and development wise. Then were kind of the human characteristics, the brain capacity and language when they first occurred and when they first occurred in a child. And then finally, the more cultural phases, when I did the log scale of life, most of those were on the cultural side, right? Going to kindergarten and then becoming an adult and working type of thing. So I think that at least those three had to be in there. And when I kind of came up with that estimate, it's kind of a speculative type of thing. And I had to decide, there's many ways of potentially calculating this, right? So what aspect do I focus on? And there were many options, and I'm sure that in various fields they could come up with other ways of approaching that same problem.
Thank you. Emiro, if I could ask you to unmute yourself.
Yes, yes.
And then who's
I was
answering it,
waiting.
I'm gonna ask them to come up here and speak.
Yeah.
'Cause it's the mic that picks us up.
So it's a very simple observation actually. It is that I believe that one of the problems with the definitions of complexity is that you are trying to define complexity with a one-dimensional number. And this is a multidimensional problem. Complexity is multidimensional. I believe that there is a need to combine different measures of complexity in a kind of vectorial measure. Well, of course, there will be the problem of seeing how you solve the questions of additivity that such a measure will have, and so on. But I believe that that is the direction to follow. That's my comment. Thank you.
Yeah, I would agree. I don't know if I had time to go into it. But I do mention, I maybe didn't have time, that complexity is multi-axial. I mean, humans are more complex than other animals in how we process information and store it and manipulate it. But other animals obviously are better at echolocation or flying, of course, without jets and all that, but so forth. So yeah, there's many different considerations, and complexity really is like life. You have to define its characteristics. And as I mentioned, the more characteristics you list that are required to be a complex, the more specific you are, but the less sensitive. You're going to miss some systems that people might consider to be complex, like the internet. It didn't pop up out of the ground, humans created it, but it's still, in many people's idea, it's a complex system. Whereas, life somehow self-organized, self-regulates. It's the epitome of complexity as well as ecosystems. So yeah, I totally agree. There's many different aspects of complexity, and just it's not a single axis. It's many different considerations.
If there either, I don't want to cut it off. Any final questions here?
I'll make one.
Okay, Todd, please come on.
About both these. So first of all, I appreciated Davidson's point. I'd like to talk more about that, because I think this idea, if we could generalize that idea of taking the 7 religious disciplines and sort of bringing them together and finding the overlap, if we could do that even more generally and see what they all have in common, I think that's kind of what I had in mind, and it sounds similar. So I'd like to talk more about that. Just off the top of my head comment about the information and energy, that just from a fundamental physics point of view that might be useful is, I wonder if at the core of it, there's kind of, to store every bit of information that you want to store requires a certain amount of energy, right? So, but there are many, but not all energy is being used to store information. So I wonder if something about the question of when it's useful to use something like free energy rate density comes down to that, right? And if you're comparing apples to apples where they're storing the information with the same amount of energy, then it's a fair comparison. Whereas if those are not connected, which they may not be, then it's not. So it'd be just interesting to look at, maybe, if you haven't already. That's it.
Okay, if there are, oh yeah, please come on over. And then again, if you can speak into that.
This one?
Maybe.
Okay, my support. Yeah, this is a question today because when he said what the topic was, what kind of universe do you want? And I thought you were going to talk about a design universe. I read a little bit about it, and you didn't go there. I know why, but I'd like to know why you didn't go there. Because one book I read says that electrons are perfect. That is, the charge between them is just right. If they had a bigger charge, then the universe would just be one big gray mass. And if the charge of electrons were less, the universe would just be a gaseous existence. So it's, you know, somebody got it just right. That's all there is.
Very good. Thank you very much for that question and comment. That does make a big difference. And so that kind of gets close to the anthropic principle and how do you understand that? And so there have been a lot of discussions about how fine-tuned the parameters are, right? Some people saying, yeah, they're fine-tuned. Others saying, well, no, they're not really fine-tuned. I point to that Clement Vidal, who was at the Amsterdam IBHA conference, who kind of went into that in a quite deep fashion, and pretty much said, well, we really don't know. After very, very well documented, we don't know. But that it is correct, for example, on the charge, I mean, there's a symmetry involved. And boy, if those charges were, you know, between a proton and like a quark, 1/3 of a charge or 2/3 of a charge, right? Whereas an electron is 1. Well, if that was just a little bit off, you know, you'd have tremendous problems because, you know, the forces would not cancel out and you wouldn't get a lot of these subtleties to it. But I kind of wanted to approach this not from, you know, you're a designer, but to think about, you know, what do you actually need in the universe as opposed to like, here it is, you know, you're given these 4 forces and this is what they do, and you're given these particles and this is what they do. It's like, well, let's think about it. What's important about these forces and particles? And so it's still, I think, a topic very much up for discussion in there. And I think this is just, you know, maybe perhaps one way to approach it a little bit differently that comes up with other questions. Thanks. I just wanted to, again, Fred Adams, I believe at University of Michigan, he's been involved in looking at various, you know, part of this anthropic principle discussion. And he says things aren't really all that well fine-tuned, especially for stars. He's looked at, for example, different strengths of the weak force, and he said, you know, you get different universes, but they have kind of properties that might support complexity in there. So that's an ongoing discussion at that level also.
Did you have a question?
Carl?
No. Okay, well, the question is for Todd. I was just wondering about this dark matter that you said. What is the strong argument that are raised by physicists against having different gravitational constants on different scales of the universe? I mean, it seems to me like the more natural explanation, but there's something I don't know here, I think.
Yeah, that's a very good question. So you're thinking about like the Mond type theories, whether the gravitational or even something related to that.
I'm not that familiar with
Okay.
it, but
So correct me if I'm misunderstanding, but the way I'm interpreting the question is that why do we focus on there must be some other matter there,
Yeah.
as opposed to, well, maybe the gravitational constant is different in other places, or like one of the patterns that shows up is that it's only at very small accelerations, like I think it's on the order of 10 to the minus 10 meters per second squared, you know, compared to like 10 meters per second squared for acceleration of gravity on Earth, where most of the significant effects show up. So there is definitely some consideration. It's a minority, but there's some consideration about whether there could be different laws of gravity, or, you know, or maybe tweaking the gravitational constant in different realms or something like that. But there are a lot of, against the concordance, right? There are a lot of things that you have to be, the equivalence principle in general relativity seems to hold. And so you have to, it's not always easy to make it all fit together. But that is, I think it's a valid point that's still under consideration. And I guess at the other end of the scale, the observations, there's getting more and more, like the bullet cluster data seems to show that it really does need something that can be, that there's other matter that doesn't track the matter we can see, which is what would happen if it was just a change to the gravitational constant, if that makes sense, right? There'd be like a seed for the gravity. So it's still an open question. That's a valid thing to ask about. Yeah.